Bismillah ar-Rahman ar-Rahim. This is lecture 14. It's a continuation of the previous lecture on positive definite matrices, and we now take up the case of n by n matrices. We first state the conditions for the matrix to be positive definite. So when an n by n symmetric matrix has one of the four properties, it has them all. One is all eigenvalues must be positive. Two, all the upper left determinants must be positive, and all the pivots are also positive. And fourth, x transpose A times x is positive except at x equals 0. So the matrix is positive definite. So we take up an example to prove these. The matrix A is the tridiagonal matrix we used before, with 2's on the main diagonal and -1 on the upper and lower codiagonals. We'll see that this will be positive definite, because if we use Gaussian elimination, we eliminate below the first pivot. The multiplier is -1/2. So we put it in the matrix L to 1, and eliminating below the second pivot, the multiplier is -2/3. We put it in the matrix L. So we arrive at U with the pivots on the main diagonal. See, all pivots here are positive. The pivots are the upper left determinants, okay, each divided by the previous determinant. For example, the first upper left determinant is 2, and here the upper 2 by 2 determinant is 3. So it is divided by the previous one, 3/2. And the last pivot is the determinant of the 3 by 3, okay, which is 4, divided by the previous determinant, which was 3. Okay. So all the upper left determinants are positive. Okay. And the eigenvalues of this matrix we have calculated before, and they were 2 plus root 2, 2 minus root 2, and 2. They are also all positive. So that completes the tests 1, 2, and 3 above. And we can write x transpose A times x as the sum of 3 squares. Okay. X here is x1, x2, x3. Okay. As a row vector, times A times x as a column vector. And we can write it as a sum of 3 squares in this form. See, x1 minus 1/2 x2 squared. This is the first multiplier inside the square, and 2 is the first pivot. The second term is 3/2. It is the second pivot, multiplying x2 minus 2/3 x3 squared, and minus 2/3 is the second multiplier. Okay. And the last pivot 4/3 times x3 squared. So outside the squares we have the pivots, and inside the squares we have the multipliers in L. So that proves positive definiteness for an n by n matrix for the case of 3. Now we consider an important application of positive definite matrices and positive definite quadratic forms, and also an application of the principal axis theorem, which is connected to the Q lambda Q transpose factorization of A. Okay. And we consider the problem of the ellipse here. The equation of the ellipse, if it is written with respect to the major axis and minor axis, that is, the ellipse is aligned with the coordinate axis, it is the standard equation of the ellipse, x over a squared plus y over b squared equals 1. But if the ellipse is rotated, the coordinates are mixed. See, for example, if we take this equation for an ellipse, 5x squared plus 8xy plus 5y squared equals 1, this is the equation of a rotated ellipse. The lined up ellipse, if we line it up with the coordinates, okay, it means with the major axis and the minor axis as new coordinates, okay, it will take up the standard form. But now the transformation from here to here is done by means of a rotation matrix that will rotate, okay, the ellipse. It will rotate the axis. Interestingly enough, the major axis here is one of the eigenvectors of a matrix, and also the minor axis is another eigenvector of the matrix connected with the rotated ellipse. You know, this form is LDL transpose. You can write it as X transpose times A times X. And the matrix A here, you can find out that the matrix A is 5, 4, 4, 5. It gives this, okay? So to see that this is true, we calculate the eigenvalues of the matrix A from A minus lambda I times X equals 0. The eigenvalues are the determinant of A minus lambda I equals 0, which gives lambda squared minus 10 lambda plus 9 equals 0. So we have two factors, lambda 1 equals 1 and lambda 2 equals 9. And the corresponding eigenvectors for lambda 1, 1, it's x1 equal to 1 minus 1 by substituting in this equation. Okay, and for lambda 2 equals 9, it will be x2 equal to 1, 1. These are not unit vectors, so to get the matrix Q, we make them orthonormal by dividing by the norm of each vector, which is root 2. So this is Q1, 1 over root 2, 1 minus 1, and Q2 is 1 over root 2 times 1, 1. So now we form the factorization of A, Q lambda Q transpose. So A, which is 5, 4, 5, 4, 5, is equal to Q times the diagonal lambda times Q transpose. So if we multiply by X transpose, which is the row vector xy on the left side of the left-hand side and also on the right-hand side of this equation, and we multiply by the column vector xy on the right of each side of this equation. The left-hand side is X transpose AX, which is 5x squared plus 8xy plus 5y squared, and the right-hand side will be, when Q is multiplied by the row vector xy, it gives the row vector x minus y over root 2, x plus y over root 2, multiplied by lambda, and then Q transpose multiplied by the column vector xy is the column vector x minus y over root 2, x plus y over root 2. So multiplying these out, we will get 1 times x minus y over root 2 squared plus 9 times x plus y over root 2 squared. Okay, so this is Q lambda Q transpose, and on the left hand side it is LDL transpose. If we complete the square on the left hand side, we can find the pivots here multiplying the squares. Okay, so here we have the pivots multiplying the squares, x and y, and here we have the eigenvalues multiplying the squares. Okay, both forms are equal. In fact, if we expand these here, if you expand the squares, you arrive at the left-hand side. So both are equal. So LDL transpose, it's actually A, it's equal to Q lambda Q transpose. These are two different forms, okay? Two different representations in two different coordinate axes, okay? So here it is, LDL transpose equal to Q lambda Q transpose, where capital X is x minus y over root 2. Okay, it gives the major axis, and y, capital Y, is x plus y over root 2. It gives the minor axis of the ellipse. Okay. This is the principal axis theorem, and this is an example of the invariance of physical laws. The same function, okay, is represented in two different systems, two different coordinate systems, and they are equal.